kind of just get started here. I'm going to go ahead and start recording. Hello, everybody. Thank you guys for joining Reimagine 2020. It's been a fantastic 4 days. If you didn't catch Bruno, he has an interview. I think that was day one, probably at the beginning part of the agenda there, and you can find that on the website, Reimagine 2020 website. We have him back for an exciting workshop, feel free to ask questions. There's a Q&A here, and we'll leave some time after for any questions as well. Bruno, thank you for taking the time out of your day to come join us and host this workshop. I'll go ahead and pass it over to you, and feel free to make an introduction of yourself and your name and what you'll be doing today, and you can go ahead and get started.
Yeah, sure. Thanks, Adam. All right. Hi, everyone. So today we're going to be going through Substrate, and that's a framework for building your own blockchain. My name is Bruno, and I work at Web3 Foundation as a technical educator. And my job there is basically to come up with proofs of concept, come up with ideas for people to develop, and attract developers to our ecosystem. And this is done through teaching people how to develop for our ecosystem, explaining the technical things that we've developed or are developing, and just showing people how to interact with the Web3 ecosystem that's coming out of the Web3 Foundation. You can always add me on Twitter, Telegram, or LinkedIn, or via email. It's just bruno@web3.foundation. If you want to catch up after this workshop or about anything else in regards to Web 3.0, I'm always available for a chat, and we'll help you through different things if you have any questions. So this is a TLDR for building your own first custom Substrate blockchain. And the code itself is going to be fairly simple. It's going to be the first part of this workshop, I'm going to explain what Substrate is, why it exists, and what we're actually building there. And the second part will be diving into code. So without further ado, I would like to get started, and if anybody joins after the fact, then they can always catch up. It's not going to be very difficult for them. So at Web3 Foundation, and that's a nonprofit foundation in Switzerland, which is developing the Web 3.0 ecosystem. We believe in a decentralized and fair internet where users control their own data, identity, and destiny. What does this mean? It just means that you are in control and not a third party. So your data does not reside on a third party server unless you send it there. And you always have the ability and right to revoke it. Web3 Foundation is actually the research laboratory and funder of the Polkadot ecosystem and the Polkadot blockchain, which is launching soon, later this month. And the Polkadot Network is one such blockchain which enables the Web3 ecosystem to kind of come into existence. The Polkadot Network will be used to connect different blockchains into one big ecosystem. So it's going to be like a major hub for them to talk through. And by doing that, it will connect all of these different, very application-specific chains together. Like, for example, if you like Bitcoin, you can still continue liking Bitcoin, but you can now also use it on other blockchains. If you like programming stuff on Ethereum, you can do that, but you can now do it with Bitcoin, which adds more value to Ethereum itself. And this all happens through Polkadot. So the Web3 Foundation is actually funding the development of Polkadot, which is itself coming out of a lab in Berlin, which is the Parity Tech company, which is developing our infrastructure right now. We are, of course, open to other companies joining, and we are giving grants out constantly for other companies to develop other alternative implementations. So that's in short about Polkadot. So now what we're going to do, and what I should mention here, is that Polkadot is a Substrate-based chain. So Polkadot itself is based on Substrate, this framework that we're going to be using. And this framework came out of Parity because they've developed a lot of other blockchains for a lot of other companies. And they realized that they can stop repeating their work and build a framework instead. by deciding that they should kind of abstract these things, they came up with Substrate. And so we'll see what Substrate entails, but there are currently around 10 or so chains based on Substrate in production, with more coming out every week. And most of those will eventually be connected through Polkadot to one another. Now, if you want to get started with the workshop, and if you want to follow along with the code, I highly recommend that you run this command if you're on any kind of Linux or OS X machine. Or for Windows, there are instructions at bit.ly/substrate Windows, but I do not recommend this. So we do not officially support Windows. It is better to use Substrate in the Windows subsystem for Linux environment, where you get a Linux system running natively on Windows. So you can actually execute the upper command. This will install all the prerequisites that you need to develop, and it actually takes a while to get them installed, so it's just in time to until I finish the theoretical part, it's going to be done. This is a one-time process, so don't let it scare you, but it can take a while. The second part of the environment setup, and please let me know in the chat if I need to come back with some links, or if I need to kind of backtrack or anything. I think you'll have to use the Q&A though for that or something. But please let me know if you missed something, and I'll gladly backtrack to that. So for the environment part 2, you will of course also need Node.js, because we will be building a user interface for interacting with the chain, preferably installed via NVM, which is a Node version manager. So you can have multiple Node.js versions installed on your machine without them conflicting with each other, which is a very frequent problem with Node.js. You will also need Yarn installed globally, which is the package manager for Node.js, and that'll help you install dependencies and other stuff when we start building the user interface. So please make sure you do that if you'll be following along. So once the substrate command finishes, the get substrate command finishes, you should update your Rust by running rust update nightly, rust update stable, and then finally rust up target add wasm32 unknown toolchain nightly. What all of this does is enables the compilation of the code in the latest nightly experimental versions of Rust, and it adds a wasm compiler to the mix so that the code that we are writing can be compiled to wasm. And that's a very important detail that I'm going to mention a little bit later. Because that's a big part of the magic of Substrate, the wasm thing. To get started with the code, to download the template, you should run git clone, so this command. And actually, I want to try sharing. Adam, if you're there, can you help me share something in any kind of chat or something? Ah, we do have chat. Good. Sorry. Okay, I'm going to share some links here. And if you're following along, and if you want to follow along with the code, I'm going to share a preparation post for you, which you can follow to get up to speed here. So if you follow this post, this is going to take you through all the prerequisites and through all of this that I'm showing here. So I don't have to go through it here in the slides. So please go through these steps while you're listening to the presentation. The whole compilation process of the node template. So the node is the software that's running the blockchain, and we have to download it and we have to compile it. And on most machines, the compilation takes around 20 minutes if they're a desktop machine. On laptops, it's usually closer to 30 to 40 minutes. And on like Windows native, it'll be around 10 minutes. So you can expect, depending on your machine's power, it'll be around 10 to 40 minutes to compile this. But this luckily only has to happen once. Every time you change something in the node later on, as we will do, your recompilation process will take only like a minute or two. And we're going to demonstrate that as well. So please follow that post. It'll go through everything I've mentioned here. Alternatively, if you don't want to do that, you can open this URL, and I'm also gonna paste this in. So this URL contains pre-warmed up virtual machines on a cluster that we have prepared for you. And if you can see my screen hopefully, and you will see this playground open now. So just click on experiment, and it's gonna be loading. And what is going to open is an interface very similar to Visual Studio Code, in which you will have the node and all the prerequisites already installed and working, including Node.js, including the front-end template, and it will also be pre-compiled, so you won't have to wait for the compilation step. This is taking so long now because my VM, it seems, is not warmed up, but let's give it a moment and see if it fires it up. It should work for you already, hopefully. Let's see, one moment. All right, let's let it load in the background. We'll see. We'll come back to it later. Anyway, it's either this URL or the post for preparing the environment that I shared a little bit earlier. Okay, let's move on. So what is Substrate? Substrate is an open source, modular, and extensible framework for building blockchains. And like I said, this came out of Parity, who have developed these blockchains for other companies. And then I realized that, look, guys, we're building a database from scratch every time. We're building networking from scratch every time. We're always repeating this work, and it should be abstractable, right? And so what they did is they made a framework in which they extracted all of these layers and put them into something that's reusable. So with Substrate, you download this template, basically, this framework. And what you get is you get a database layer, you get a networking layer, you get a consensus engine, you get a transaction queue, and you get a library of runtime modules, which are basically plug and play. So you can essentially plug and play the custom functionality into your chain. Now let me just check if my VM loaded. Ah, it did. Okay, so this will open interface familiar to anybody who's used Visual Studio Code. Essentially, you click here on the files on the side, and inside you can close this marketplace down. Inside the workspace, you will find the Substrate node template, and you will find the Substrate front-end template. So the front-end template is the basic UI we'll be customizing to interact with our chain. And the node template is the software that's running the chain itself. And we're going to be building on this. We're going to be programming things into this. We can keep this open. These machines are alive for, I think, 24 hours. And then they will get wiped. So don't put anything mission critical on them. And if you do, there's always the right click and download. So download your stuff if you write something important here. Anyway, you can work through this. I'll work on my machine locally, but I'll also tune back in here and maybe demonstrate something here. The experience is exactly the same. There's literally no difference if you develop locally or here, only that when you're developing here, you don't actually keep the sources, right? Unless you commit them to GitHub. All right, let's go back to our presentation. Oops, sorry, looks like the links went to the panelists and not to all attendees. Sorry about that. There we go. Okay, this should be helpful. So the first link is the one that'll prepare your environment, and the second link is the link to the playground that'll fire up the VM for you. Remember to let me know in the chat if anything's missing, or in the question and answer part. I'm keeping an eye on it on a second monitor, so I will see it. Just let me know if anything's wrong, if you can't read something, if I need to go back, forth, and so on. So now we have Substrate, which is a framework, and it has a library of runtime modules, which are plug and play for this framework. Let's take a look at that. So the Substrate runtime is the block execution logic of the blockchain, aka the state transition function. So when you have a blockchain and you have one block and then you have another block, something had to have happened to move from one block to another block. And that's called the change of state. And the function that changed that state is called the state transition function. So when you're building a blockchain, you have to kind of tell the software the logic of changing from one block to another. What are the conditions? How does a block change? How does a block interpret new data so that it can become the next block, right? How does the blockchain grow? You have to have these rules in there. And in Substrate, this runtime is composed of these modules. So what we mentioned before, these library runtime modules, this runtime is composed of these different self-contained modules that are highly isolated and very, like they're developed as packages basically that you just pull in. So what does that mean? Well, we call these modules palettes. And palettes built with frame. This frame is a system for building these palettes. It's like a framework for building these palettes, right? Substrate is a framework for building blockchains, and frame is a framework for building palettes. And we'll build a palette today. And by building a palette, we'll actually build a blockchain. So it's all nested, you see. Now, for example, here, this runtime up here is composed of system, babe, pseudo, grandpa, indices, timestamp, and balances. Now, these are all different runtimes. System gives you core functionality to the chain so that the chain is aware of some core things like, I can actually demonstrate this. So this hooks into a currently live Substrate chain, and I can check this out with chain state. Constants, for example, the system is already pre-selected, and this is our system palette. Let me know if you can't read this, if it might be zoomed out a little bit too much. But anyway, constants system, and now I can check the maximum block weight. So this is how many transactions can fit into a block. If I click plus, it just returns to me the maximum block weight. So this is the data that you have in here. Then I can also have extrinsics, and this is like transactions. This is submitting transactions. And there's a command called setCode on this system palette. And the setCode command lets me upgrade the runtime itself. And we'll talk more about that later. So each of these palettes is represented in your chain, and you can interact with each of them independently, but they're all compiled into one single runtime when you select from some of them which you want to use. The balances palette, for example, lets you have a balance on chain, so you can represent who has how much money, who has how many tokens. The grandpa palette finalizes blocks, so the chain cannot revert. The timestamp palette just tells you what time it is. The pseudo palette is like an admin palette, which lets you do administrative functions on the chain that you would usually have to run through governance. And the democracy palette, which is not included in this runtime, is the governance itself. So it lets you have on-chain governance where people vote with their tokens for changes of the chain itself, and we'll also go through that. So the runtime is composed of these palettes and then compiled into one little WASM blob, which then contains the logic of all of these palettes together and essentially tells the chain how to progress, how to move from one block to the other. So for Substrate development, we have the Substrate node template, and that's actually a working Substrate node. If you just compile and run the Substrate node, and actually let me show you how that works. Let's go to here. Fresh copy of the template. All right, so I have here a fresh copy of the template. This is the exact same thing that you have in the playground if you opened it. If you open the terminal and then you have the terminal accessible here, you can go to CD Substrate node template and you're in the same folder. So I have the same thing here, and let me just zoom in a little so it's more visible. All right. We're now in the folder of my Substrate node template. And when you build a Substrate node, and the build happens with the command cargo build release, you see that it's compiling my node, right? Now, this number, 288, 291, or 654, this is a number of crates. This is a number of modules included in this Substrate node. And once it compiles all of them, it'll end up with a binary, with a program that you can run. When you run that program, you're actually running one node of your chain. If you run that node in a development mode, then you can run just one and it'll work. It'll simulate a chain. But if you run it without development mode, you have to share it around. You have to give it to other people, and they have to connect their own nodes, and then your nodes have to find each other, and then you get a blockchain. Because you can't really have a blockchain with a single node. It's not a real blockchain. So once this compiles, we'll be able to run it, and we'll be able to see what our blockchain actually looks like when it's running. We'll be able to inspect it. Now, so The node template, when you run it, it has these basic things in it, right? It has the babe for block production. So this is what decides which authority, and authorities are the validators of the system. Baccarat and mainly almost all substrate-based chains are proof-of-stake chains. This means that in order to produce new blocks in this chain, you put some stake down into the system, and you basically promise the system that you're not going to do anything malicious. And if you do something malicious, the system can take your money away. So this is the proof-of-stake system. So Babe has some rules on who of the stakers is currently responsible for producing a block. So Babe dictates who's building a block and based on which other block in the past. Grandpa finalizes these blocks so they can't revert. Sudo is the admin key function, which I'm going to demonstrate later. Indices just indexes the accounts in the system. This is actually unnecessary and will be removed. And balances lets you have accounts. This runtime is compiled to WebAssembly and is used for achieving consensus between the nodes, which are connected to each other through libpeer-to-peer. And libpeer-to-peer is this networking standard that's fairly new and very powerful. And libpeer-to-peer is used to make these nodes find each other on the wide area network and to get them to connect to each other and to to form this chain so that you can actually run a chain. And the Substrate node template is what we're going to be using as a starter chain. And we're also going to be extending it with custom logic and with a custom palette on top so that we get a custom blockchain. Furthermore, we're also going to be using a Baccarat.js apps. So the Baccarat.js apps, now the really great thing about substrate-based chains is that they all expose metadata about the chain itself, which means that they expose one data structure which contains all of the errors, all of the events, all of the palettes, and all of the functions that exist, all of the constants that exist in a chain. And any UI that reads this metadata can actually use this information to construct a UI for that metadata, which means that no matter how much you customize your substrate chain, a UI that is configured to generate a UI based on that metadata will work with your chain. And one such UI is the Baccarat.js apps UI, and I'll demonstrate that now. So this is the Baccarat.js apps UI, and it is currently connected to the Kusama chain. I'll explain Kusama in a minute. And you can see that Kusama is on block 2.4 million. And you have all of these options on the side. So you can do proof of stake on this chain. You can stake your tokens and earn interest on it. There's a democracy palette where some things are being voted on. So it's a little slow because it's loading a lot of information on the staking screen. There's no caching here. This is a decentralized app. You can run it locally on your computer. So it all happens live, and that's why it can sometimes get stuck. So this is the democracy palette. And this shows you what is currently being proposed on chain. For example, proposals are made by just regular token holders. And this proposal is suggesting that we add a registrar to the system. A registrar is an account which can verify identities of people on the chain, like this one. This is a verified identity. This proposal will increase the number of validators in the system from 250 to 350. So that's also pretty powerful. But these are just proposals. To be tabled as referendums, they need to be seconded. And once they're seconded, they become a referendum, and then a referendum is voted on. If this referendum passes, this is going to increase the validator count from current 250 to 275. And then this one is going to further increase it to 350. But this is an example of the democracy palette, which demonstrates that the votes of the community can influence what happens to the chain itself. The chain's logic, the chain's code can change if people vote for it. And this is part of the magical forkless upgrade method. In typical blockchains, when you need to upgrade a blockchain, you need to execute a hard fork. Let's see if this is done. No, not yet. So in typical blockchains, we need to execute a hard fork. And a hard fork is when you compile the blockchain into a new binary, into a new node, and then you distribute it to other people. They have to download it, they have to replace their currently running binary, and then everybody who didn't upgrade, they stay on an old fork, they get left behind until they upgrade their binary, and then they catch up, and then they rejoin the network, right? But in a fairly decentralized network, this is very difficult to do because you have no means of reaching all of these anonymous users who are running your software. Well, we said that the runtime is compiled into WASM, into WebAssembly. And when it's compiled into WebAssembly, that WebAssembly code is stored on the chain itself. So all the nodes running this chain, they're reading from the chain the code which they're supposed to execute. Now, these nodes are going to have their native code written in Rust, and they're also going to have this on-chain WebAssembly code that is WebAssembly. If the WebAssembly code is newer than whatever they have in native, then they're going to be running the WebAssembly code. Then if somebody upgrades their native binary, their native code, their binary, to the newer version, which also has the native code identical to the WebAssembly code, then they just get a performance boost because native code is always faster than WebAssembly. But WebAssembly takes priority. So anything that's on chain will be run first. And this is the wonderful thing about substrate-based chains. All of them inherit this ability, and all of them allow you to upgrade the runtime of the chain itself on the chain itself while the chain is running. And we're going to be demonstrating this in a bit when we build our own chain. So you can compile a new version of your chain, you can upload it to the chain, and all the nodes that are currently connected are automatically going to update. There's no need to download new binaries, there's no need to replace programs that you're running. They will all automatically be up to date with your newest version of your chain, with whatever you've developed. And that's pretty powerful because it lets you keep the chain running despite people not being ready to upgrade. So what else is here? Well, we have the node template, right? And we have the Baccarat.js apps UI. Oh yeah, I wanted to demonstrate how that UI changes. So now we're connected to Kusama, and it has these options, right? It has the Treasury, the technical committee, parachain, society, and so on. So now what happens if we connect to another chain? There's a list of chains in the top left menu. You can connect to different ones. And these are all substrate-based chains of different types. Now let's connect to Edgeware. Edgeware is a smart contract chain based on Substrate. If we connect to this, the page reloads, and suddenly we get the following. We get a blue bar up here indicating a change. We get a different logo, we get a different block number, and we get a different sidebar. Notice that there's no longer society, and there's no longer some other options, but now we have contracts. And contracts were not available on Kusama before because Kusama is not a smart contract network. So by just providing different metadata, the Edgeware node to which this UI has connected made sure that the UI changes and accommodates this new chain. And this is the real power of Substrate's metadata emission, because any client that connects to the chain instantly gets all the information about the chain from the chain itself. And it can then, see, this is now throwing an error because I stayed in the contracts tab, which doesn't exist in Kusama. So let's just go back to Explorer. So you get this metadata, and every client that connects to any node running that chain will know everything about that chain. And this includes wallets, this includes simple interfaces like this Baccarat.js apps. This includes really anything else. This includes other nodes as well that need to find out about the chain that they're joining. And this is a really powerful mechanism. We'll also be using the Substrate frontend template. And this is a React.js project with pre-built components to do some things that we want to do with our chain. This is a very, like a super rudimentary version of Baccarat.js apps that I just showed you. This is a very simple interface on which you can't really do much, but you can do the essentials. And this is highly extensible. It's a very lightweight program. The Baccarat.js apps that I just showed you, this part, this is super heavyweight. Like, it's a very big application because it tries to accommodate everything. But this is very specific and very customizable to work with just your chain. And that's something that we're going to be playing with as well. All right, so for the basics of Rust, I'm actually not going to go through this, so we can go to code as soon as possible. But Let me just see what we can discuss here. Everything else we're going to demonstrate. Okay, this. So when you're building any kind of logic, any kind of customization in a palette, in a blockchain based on Substrate, you will mainly be using macros. And macros are magical bits of code that generate other code, as you might know. There are 4 main macros in palette development. Declare storage will help you declare what you are storing and how you are storing that data. Declare module will help you declare all the functions that your palette will be able to expose to the outside world so that you can call them through this extrinsics interface so that you can actually invoke them. You can see here these are all different palettes and all of them have their own functions. So this is something that we are going to develop as well. Our palette is going to be one of these options and it's going to have its own functions here. That happens in declare module. Declare event will declare all the events that can be emitted by your chain. So example, when I send a balance, when I send some tokens to somebody else in the Kusama network will emit an event which says balance transfer from this guy to this guy for this many tokens. Sorry. Declare error will declare errors that your palette can encounter. So when something happens that doesn't really, that shouldn't really happen in your code, or that the user did wrong, the declare error macro will help you document these errors and expose them to the public. They are difficult to read because a macro into which you write like 200 lines of code will get expanded to maybe 1,200 lines of code. And that's the magic of macros, right? They take some maybe odd syntax in, but put out a lot of really good and proper code. The macro special power is that they can use custom syntax. They don't have to, so Substrate is built in Rust, the programming language Rust, but macros are not typical Rust. They're kind of Rust-ish, but they deviate enough from Rust to make them simpler to use. And you'll see what we mean by that. So they're just used to simplify the creation of modules, of these palettes. So for the basics of runtime development, I want to show you this skeleton of a module. We have the imports at the start of every palette that we're building. Then we have a public trait definition, which is just some boilerplate code that you will simply have to include in every palette that you're building. Then you have the 4 macros, and then you have the implementation of the module itself. That's all there is to it, and you'll see that in 100 lines of code we can build our custom palette. This we can skip, this we can skip. So this is all how these things are used, but we're going to go through these and like in a very manual process so you can follow along. I hope your environment has warmed up. All right, let's build a proof of existence chain. So a proof of existence chain is a chain that guarantees the existence of any data at one point in time. So if I have a song, if I wrote a song and I decide to copyright it, I will hash that song. So I will pull it through some advanced math. I will get a hash out of that, and a hash is just a combination of letters and numbers of a fixed length, so like 64 characters of letters and numbers. And that hash I can store on the blockchain. So if you run the same data through the same hashing function multiple times, you will always get the same hash out of that function. And that's useful here because if somebody 5 years later shows up with my song and says they wrote it and they want the royalties, I can prove that they didn't write it because I'll just give to the judge my song, the hashing function used to produce the hash, and the blockchain entry where this proof resides. Since the blockchain will never lose data, it will always keep it around, my hash will still be living at a certain block in the past. And since we know when a block occurred on the blockchain, I can prove that my song was registered on this chain 5 years ago on block XYZ and under this hash. And this basically helps me prove ownership of my content of any file. It's like a digital notary, right? And we're going to build that. So first, let's start the chain. My node has probably compiled. It has indeed. And it took it 12 minutes. Weird, seemed longer, but okay. Now, let's first run the chain, the basic node template as it is. And we do this by targeting .target, release, and then its node template. We can run this chain with the dev flag. If you run it with the dev flag, then it's going to run in development mode. If you're running the playground, you can use this substrate start node. You can just use this, or you can type it into the terminal, doesn't matter. So substrate start node, it's going to work exactly the same as my own local one. So you can see here, it's starting to work. I'll also run my local one, and don't forget to add the --dev flag if you're running this, so that it can open up a development chain. A development chain means that you don't need multiple nodes to run it, and B, several accounts will be pre-generated and unlocked and preceded with some fake money so that you can test them around. There we go. Now, don't be fooled into thinking that these two nodes will connect. The playground one is completely independent from the one that I'm running locally, even though their logic is the same. Why? Well, because I didn't really connect them to each other, and they don't know about each other, and they didn't start from the same genesis. They didn't start from the same data that starts the chain itself. So these are two different chains running independently. Okay, let's try and connect to my local chain now. So if we go to polkadotjs.org/apps, I'll share this link in the chat. polkadot.js.org/apps, so just like this. We end up at the Explorer for Kusama, but we want to connect to our own chain, which is running now. And if you're running on the playground, you can connect it. You can actually, if you do start frontend, you will see the URL here, WSS:// something long, and it ends with /WSS. Copy this. This is your URL on the playground. My URL locally is just localhost, so I'm going to use that. I go in the menu to the bottom, and there's the local node. So that's just 127.0.0.1 and port 9944, which is the default port for Substrate nodes. If I save and reload this, this is going to connect to my local chain. And you can see now it already says that this is the development chain. It's on block 18, now 19. The blocks are being produced and registered in my block explorer. I can look at accounts, and you can see here that we have several accounts: Alice, Alice Stash, Bob, Bob Stash, Charlie, Dave, Eve, and Ferdy. All of them are unlocked, but the first four also have 1.1 million tokens in their accounts, so you can spend those and send them around. Let's send some tokens. Let's send 1,000 tokens from Alice to Bob. Let's see how that works. Send. It'll ask us for the amount, 1,000. So from Alice to, you select it here. I'll find Bob, Bob. There we go. And make transfer. Sign and submit. Alice is unlocked, so the transaction just goes through. There we go. So Bob, you can see here, he has 1,000,153, and Alice has 1,000,151. Now the reason why this is still spinning is because we are using a slightly older version of Substrate node template, and Polkadot.js org apps is using a different configuration. If we want these events to work, and this is not something you need to remember, this is just a hack that I'm going to do to fix this right now. That's going to be a wait configuration. So we go into the toolbox. We'll go into settings, metadata, developer, and we'll put here this. So you put in wait under like quotes and colon, and then under quotes U32. If you save this, then the events will start working. So this is supposed to close and emit an event of a successful send. Let's try that again. Let's refresh. Let's send back that 1,000. 1,000, make transfer from Bob. Whoops, did I say? No, I didn't say to Alice. Send it to Alice. All right, there we go. Send it back. There we go. And now we got an event, balances transfer. Let's inspect that, shall we? Here we go. So we look at the block in which this happened. And we can see here the extrinsic. So the unextrinsic is external input into the chain. So this is something that triggers a state change in the chain. So we submitted the extrinsic to transfer balances. And this extrinsic was initiated by Alice. This was initiated to Alice, destination, and the value was 1,000. Now let's see here, this is just the extrinsic that we submitted. But let's see here the events. So the event is balances transfer. This is our event. And if we inspect it, we can see that account ID Bob sent to account ID Alice a balance of 1,000. This is our event. So you can inspect the details of events here. And events like these are something we'll be configuring in the code. Okay, now our node is running successfully. It's working. We can send money around, but we can't really do much else, right? There's no other functionality. So let's work on something. Let's now, let us now inspect the file structure here. So if you open the node template, let me use my own, okay. If you open the node template folder, you will find in palettes, template, source. So this is the folder we'll need. Palettes, template, source, and the cargo toml file outside. Make sure you find these files. So it's in Substrate node template, palettes, template, source, librs, and cargo.toml. Most of our changes are going to be happening in lib.rs. And lib.rs comes with an example palette that we can already use. Here's an example. Here's how that works. Let me show you. So our chain already comes with a template palette that we can actually use and abuse. And we can go to extrinsics, and extrinsics let us compose manual transactions. So all of these options on the side are actually shortcut convenience methods for doing this. If I wanted to make a transfer from Alice to Bob, just like I did before, I could also do it through extrinsics. I would just go through, I would select Alice, I would go through balances, and then I would do transfer. And I put here destination and value, and I do exactly the same thing. Only this has been shortened and put into accounts by the developer of this UI. But in extrinsics, we have all the functionality of our chain that we can interact with. Okay, let's see that. There we go. The template module is the module that we're going to be customizing. And that's something that comes with the Substrate node template. And this is just an example. So if you click on this, two functions are exposed: cause error and do something. Let's cause an error. We select the cause error function and we submit the transaction, sign and submit. And you'll see now block is 71. As soon as it turns to 72, we got the error. It's extrinsic failed. Okay, let's check it out. It was in 71. No, it was in 72 actually. And there we go. Events, extrinsic failed. Let's inspect it. Okay. The type of the error is template module non-value, and the detail says value was none. That's a typical error, and we'll see how that's defined in the code in a minute. Actually, let's show it right now. We have here declare errors. That's an enum of errors, a list of errors available in this palette. And here's our error. So the text above, behind 3 slashes, is the text that the error emits, and the value is just non-value. And this is another error that can happen actually, which we have not invoked yet. But this is where the error is documented in our code. Let's try the other function. Extrinsics, template module, do something. And then we put something as 5. Sign and submit. And there we go. We've done something which says 5. Let's see what this did. If we inspect chain state, we can read from the current database of the chain. And now we can go through template module and we read from something. It's automatically selected for us because this is the only storage option in our entire palette. Let's check it out. Yep, it says 5. So we stored the value 5 in our sample blockchain. And this value 5 is staying there forever until we change it, right? So if I change it, template, do something to 10, go back, read template module, something, all right? And now it's 10. Okay, so this is the basic read-write operation in a blockchain that you can do with even this essential template that kind of comes preloaded for you. Now, let's customize this a little bit. For starters, we're going to delete everything from our librs file. So if you go back to this file, just select everything and delete. We'll start from scratch so that we can develop everything as if we were starting fresh. And I'll explain every line of code that makes sense to explain. So in every palette development start, you first have to declare one attribute that is simply required, and you'll just have to learn it by heart. This is the following. We will configure the following attribute. So we configure an attribute that when we are not using the feature that is the standard library of Rust, then we will configure the attribute to be no STD. And what this means is that we are not using the standard library of Rust, essentially. And that's something you just copy and paste every time you develop. It's even going to be included in the template starter, so you didn't need to worry about it. But I want to explain it. The Rust standard library is quite heavy, right? And if you compile that to WASM, to WebAssembly, that's going to be a way too big file to include on the chain. And so those forklift upgrades that I talked about are not going to be an option. Instead, we have developed, Parity has developed a different standard implementation, of these standard things that are expected from Rust. And those are the ones you use when you're developing. So these standard tidbits will have to be included from time to time, and I'll point them out. But this is something that you will always be copy pasting. You will never have to worry about knowing this by heart. It's just something, it's just one of the oddities of developing this in Rust. And every language has these, but you know, it's just something that you have to get used to. Then we will do our imports, and imports tell us which logic, which other code we're going to be using. So frame support, and frame support is a palette actually, which contains our macros and some other helper methods to help us develop our blockchain. And those are going to be, like we mentioned in the presentation, declare module, it's going to be declare storage, it's going to be declare event, and it's going to be declare error, the 4 macros. But it's also going to be 2 more things that we're going to need. One is ensure, and this macro this macro works like the require or assert function in different languages, and it just basically returns an error if something is not what you put into this macro. So it just checks that the condition put into it is true, or errors if not. And also need a storage map, which will help us store any data into our blockchain. Always end the statement with the semicolon. Next, we'll use the frame system palette, and the frame system palette contains some basic information about our chain, such as the block number, the timestamp, and so on. Also, sorry, no, not the timestamp, the block number, block hash, and so on. We will also, so we will import this palette itself, and we're going to alias it as system, so we can reference it as system in the code. And we're also going to import another function, ensure signed, semicolon. Okay. Ensure signed is a function which checks, so when you submit an extrinsic into the chain, you are the origin of that chain. You're the origin of that extrinsic. So you are where the extrinsic originated. You have to, like, if you don't make sure that the extrinsic is signed, so it's cryptographically signed, then you're basically letting anybody execute functions on your chain. You have to make sure that whatever is being submitted into the chain is also signed by the submitter, cryptographically signed, which will authorize only that submitter to execute that function. So we'll be using this to not only check that our extrinsic is signed, but also to find out who signed it. And this is also something you can expect. Both of these import statements are something you can expect in every palette. So we will also be just copy pasting this. And I can share this code later, but essentially this will come in every node template palette already pre-written for you. So you just download it and you start customizing. This is already there. Let's move on. So let's make the scaffold for our macro like we saw it in the presentation. First, we have to define the public trait called hilariously trait, and that's going to be system trait. And inside it, we are going to define that we're going to define the event type. And again, this is just something that you will be copy pasting because all the events are essentially the same. So this is something that will basically never change. It will always be the same. And if it changes, it'll just change in the template as well. So we'll never have to worry about manually changing it. So we now define the ability to emit events, one part of it at least. Now our trait, our module will be able to emit events. Now the trait part is just used to define palette level, palette wide types and constants that your entire palette, your entire blockchain will be able to use. So this is kind of like a common area for things common to every function to reside in. We'll also declare our error and leave it empty, or declare our event and empty. Macros end with an exclamation mark. So when you invoke a macro, you always end it with an exclamation mark. Storage, and we'll leave them empty for now. So this is our scaffold, our basic scaffold. Now, when compiled, the chain binary will allow clients connecting to it to request the metadata about the binary that I mentioned. And this metadata includes all the function signatures, doc blocks, everything that we've defined in the palette as well. And this is useful if you want to be told the exact error messages like we saw with the error in the template palette. So let's do something. Let's make sure that our binary can actually talk to the outside world about the errors that it can emit. And we do this with type error. So we need to modify the declare module macro. And again, some boilerplate code that you will be copy pasting is that we define a struct that is in this module. Enum call where origin, and now this brings into play the origin that I mentioned. So origin is that the origin is the origin of the extrinsic, right? Origin is the sender basically of the extrinsic, and inside this struct, we're going to define a error type and set it to the error type. So this is just boilerplate code. This is something that the macro, during compilation, the macro, when it's being compiled, is going to expand this code into something that makes sense to the compiler and everything else. But this is just boilerplate code that we simply must include. Without including this, our palette will not be able to emit errors. And we would never be able to find out why an error happened. You would see an error, but it wouldn't emit an error message. So that's why we need this. And to actually emit these events also, we need another thing configured, another boilerplate thing. There's a function called deposit event. For some reason, it's called deposit event. It should have been called emit event, but whatever. And we set that to the default. And the default is included in the macro itself. So when it's compiled, it will replace this default with the function for emitting events. And this will enable our palette, which is this, This will enable our palette to emit events of this type. And that basically replicates whatever we've seen here. When we were reading the events, you can see here the events are still going because these extrinsics to set the timestamp on every block have been successful. So this is kind of the logic of it, right? To be able to emit these events, you need to do this function deposit event equals default. And again, this is all boilerplate. This is all included in every template that you're going to download, so don't worry about remembering any of this. Now, we said that we wanted to store our data on chain, right? The claims for the files to be uploaded need to be stored on chain. Let's call them claims. When you make a hash, when you save a hash on the chain, you're claiming ownership of that file, or you're claiming that the file existed at that point in time. So let's think about how we store that data. Typically, when you store things on chain, you store hashes. You don't store actual things because it would bloat the storage, right? If you store all of the whole file, that would be like maybe several megabytes. But even though that doesn't sound like a lot, you have to keep in mind that when you're running a blockchain, there's many thousands of nodes connected in this network. And 4 megabytes submitted to the chain is 4,000 megabytes for just 1,000 nodes, right, across the world. So every little bit counts where you can save the data. You shouldn't be wasteful with it. Since a hash is always fixed length, it doesn't like bloat the state too much. It's just always like 64 characters or something. And the hash is basically just a string of letters and numbers. And in Rust, we save strings as a vector of bytes, so just a list of bytes. Then we need the vector type to store these hashes. So let's add that import at the top to use the vectors. So we'll do this like this, use. And now this is the Substrate palettes standard, SPSTT. It has a vector library inside which resides the vector type that we need. The documentation for this can be found on rates.parity.io, and this contains all of the possible code, logic, API interfaces, everything that you can think of, you can develop inside of these palettes. So this is really comprehensive. This is generated from the code, and the code is very, very detailed in documentation. So if we just go to vec, you can already find it in this list, SPSTT vec. You can see it here. So you can see here, contiguous, global array type, written vec-t, but pronounced vector. So the documentation is all on crates.parity.io. Let me share that with you as well. Chat, there. Let's go back to the code. But we can't just start using something without importing and installing that dependency first. So let's do our change in cargo.toml. The cargo.toml files define which dependencies your palette has. So this will define other palettes, other libraries that you need to import into your code to make it compile. And we are going to do something here. Every dependency has a different inclusion process, but the lucky thing is that it's always going to be documented in that palette or in that library's documentation. So in this case, we need to define dependencies SPSTT, and then we set default features. So this is necessary because of that no STD thing, right? So this is another gimmick that you just have to learn by heart. You just have to disable default features because default features will enable that standard library. We will use the version, equals 2.0, and we'll use 5.6. That should work. And we also have, actually, let's upgrade this block. So now, this is all you really need to import a dependency, but you also need to activate it here. So you activate it with sp std, and then just std. So the standard library of the SP of the substrate palettes. Again, this is all documented in the docs of in crates here. It's all documented here. You'll be told how to install this. So let's save this cargo YAML file. This is the only change we'll have to do in the cargo file. Moving on, we now have the ability to use vectors in our code. So now I forgot to mention that the default feature for this Substrate runtime is STD. So this is this. So when the STD feature is enabled for runtime, the parity scale codecs and primitives client and some other dependencies should also be using that. But you shouldn't be bothered with that. You should just, this is going to be, again, the same in every node template. And you're only ever going to be modifying the last element in all of these blocks and the last line in this STD block. And this is going to be defined by the dependency itself. Okay. So now let's add some events that we expect to emit from our blockchain. So we said that we're building a proof of existence chain, and a proof of existence chain can, so you will be able to register a claim, register a hash, so create a claim on a file, and you will be able to revoke that claim, right? So of course, we want the ability to delete something if we did something wrong, or if we, maybe we are the plagiarizer and the judge orders us to delete that claim from the chain, or for whatever other reason. So to declare events, we first enumerate what events are possible, and that's done under the declare event macro. So we will enumerate all the events in this palette, and we'll use it with a where clause where account ID, so that we have access to account ID, is system. Right? Again, this is Rust oddity that you need to just learn by heart. Account ID. So now this enum, so it's extracting, it's aliasing the account ID from the system, from system that we've imported. It's aliasing it as account ID so that we can use it easily. And we are now listing all of the events in this enum. So enum is an enumeration of events. We are now listing all of the events that we can emit in this block here. Events have two components. One is the event itself, like this, claim created, so when we create a claim. And the other, that's the name of the event, and the other are the arguments of the event. And for arguments, we're going to put in who created a claim and which claim. So that's going to be account ID. And since we said that we are saving our hashes as vectors of bytes, that's represented as vec of bytes. And comma, because this is a list. Now, events would be good with messages, right? So that they have some explanation on what they are, why they have been emitted. And we do this with the triple slash above an event. Event is emitted when someone registers. Okay. So we have this explanation. And this explanation is going to be, during the compilation step, added to that event's definition. So it's going to also be included in the metadata. And now the UI is going to be fully aware of what it can get from this event. We'll demonstrate it later. And we also need the event for revoking. So again, event is emitted when someone revoked, and the same thing, count ID and which hash was revoked. Again, comma, and even the last item in the enum needs to have a comma. So you remember this, is the compiler is going to break if you don't have the comma there. That's a rule. That's all we need for our events. These are called tuples of account ID and vector ID. We'll come back to those later. Now, let's define how we're going to be storing this data. In declare storage, we have to define how we store information. So this, the template, the boilerplate code is great. Store. Now this is going to, there's going to be some an oddity here that you also have to keep in mind. That it's not going to be included for you in the template. So this part is, so this. And then you have as template. This is a tricky part. We'll still write the logic in here, but first let me explain this. We're writing a store trait for this module, but we're saying as template module. And what this means is this is going to become the prefix under which data is stored in our chain. And this is a big deal because if somebody else develops a palette that uses the same prefix, and both of those palettes somehow end up in the same chain, because as we said, Substrate is a modular framework where you can just pull in other people's palettes as well. There's going to be a conflict in storage. You cannot have two storages named the same. So you should make sure that this is reasonably unique. Of course, everybody's usually going to be naming their storage prefix something similar to their palette. So as long as the palettes are reasonably different, these should be reasonably different as well. But since this doesn't affect really anything, putting a random string in here is just as effective and has much less chance of a collision with something else, because this doesn't really mean anything. This is not going to be visible in our metadata or in our UI. It just defines the prefix in the database itself, in the tree that is. So let's define how we save these claims. The claims are actually proofs that something existed at a point in time. So we call this proofs. And this is going to be, we import the storage map here. So this is going to be a map. The map is automatically extracted from the storage map by declare storage macro. So map, and then the map will map a vector of bytes, so the hash itself, to a tuple again, so to a set of some values. And those values are going to be the account ID from this trait and the block number. So we need to know on which block this was stored, on which block this hash has been claimed. But this isn't really like this is the basic format of the hash map. And this just maps hashes to pairs of value of this type. So to an account ID and block number. Pretty simple, right? But we need to clarify what this hash is. We need to be explicit about it. And we do this by defining a hasher for this hash. So we do hasher, and we put in the hashing function that we want to use. So this is going to be Blake2, 128. This is a default, and it's a reasonably secure default. It's the most secure hash available natively, and it's going to be the default used hash for all the hashes that are not predictable by users. Sorry, for all the hashes in general. There are other hashing algorithms that can be used if you can guarantee that the user cannot manipulate them, because then they could actually cause some hash collisions and do some attacks on the database and so on. This is outside the scope of this workshop. But again, this, you can just remember this part, copy paste it. I think it's actually going to be in the template as well. So it's just a default hasher, and it maps the hash to a tuple of an account ID and a block number. And we'll get to that block number a little later. Okay, now it's time to start writing our functions, our first function. You still define the function inside, so you define, since this is a struct, so a structure of different entities, of different types, we define our functions inside of this. And we create a function that is called create claim, because we have the event claim created. So of course we'll name our function something that's understandable, like create claim. And one thing to remember is that because of this, we're origin t origin. Every time you write a function in the declare module macro, the first argument of every single function will always and without exception be origin. Always. So you have to start with origin. The second argument can then be proof. So that's going to be the proof, and that's going to be a format of vector, a type of vector of bytes. but the origin is always the first because every function has to be called from an extrinsic, which again has an origin. This is a function, and we can start writing the body of the function. Now, if you're familiar with Rust, you'll notice that there's no return type here, and that's something that Rust insists on. There actually is, but it's implied by the macro. The macro is going to put it there, and you could write it yourself. This is actually dispatch result return type, and then you would have to end the function with OK, and then you have to like do something like this, dispatch result. But this is not necessary because the macro will do it for us, and you can't really change the return type of these functions. So that's why they were removed from these signatures, because they kind if they stick around here, they kind of imply that you can change these, and you can't really. Okay, let's write the body of the function. First we need a sanity check that our transaction was actually signed, that our extrinsic was actually signed. So we do this with ensure signed, and we put in here origin. This on its own will just emit an error if this is not successful, and the function will fail. But we want this to be something more useful. We want actually this will panic and crash the node pretty bad because we don't handle the error that's being emitted, and you need to handle errors in Rust. So by saying this, by putting a question mark at the end, we say return the value of this function or die, or die gracefully. Don't panic, just return an error and cancel this function. But what value is this returning? Well, it is actually extracting from this origin the sender of this transaction. So we get access to their account ID, to their address. This will become accessible to us here. So we'll define a new variable, call it sender, and this is how we obtain the sender of this transaction. We ensure that the origin is signed, and this single ensuring will either die if it's not signed, or it will return the sender into this variable. Then we need to, if he's trying to register a claim, register a hash, we need to make sure that this hash doesn't already exist, right? You can't really register the same hash to two different people. That goes against the proof of existence, like how it works. So here we'll have to use the ensure macro that we've imported previously, and we do this like this. Ensure. Now, again, we call it with the exclamation mark. So all macros end with an exclamation mark, and we ensure that not proofs, so that the proofs structure in our trait contains a key, and that key is going to reference proof. And if it does, we'll emit an error. This is how you emit errors. You emit errors from within this trait, and you call it whatever you want. Proof already. This is like Warren's explaining, right? So what this means is the proof structure from this trait, which is defined here, it has a function called contains key. If we pass in the proof that's being submitted in this function, this will return either true or false if this key already exists. We want to make sure that this key does not yet exist. That's why this is the exclamation mark here. And if it does, this is the second condition after the comma, this error is going to get emitted. But we haven't actually defined this error anywhere. So let's do that now. We have errors here. And again, this is going to be a public enumeration of errors. And for module, which is the code. And inside this, we will define our errors exactly the same as with events. Well, similar at least. So we do it like this. We do the message first, and then we say, this claim is already, and we define our error, proof already claimed. Again, end with a comma because this is an enum and it needs to end with a comma, even if it's the last item in the enum. We now have our error defined, and by doing this before the type error, we made sure that our palette will be able to communicate this error to the outside world when it occurs. So if somebody tries to double register a proof, this error is going to get emitted and this message is going to get printed. We'll test this out. But what is this? What is the and in front of proof? Rust has this mechanic of borrowing that also takes a while to get used to. In Rust, when you have a variable and you send it into a function like this one, this is a function and this is an argument of the function. When you send an argument into a function, that variable stops existing in the context it was sent from. So it stops existing here in this function, and it only exists within this function. And Rust will kill and remove and garbage collect variables when it's done with them in their current context, which means that if this variable were sent into this contains key like this, then we would no longer have access to proof in this scope, in this function, because it's been killed inside of contains key. It was no longer needed after this check was made. But by saying this, the ampersand means borrow. So this means do whatever you need to do with this and then send it back. And now we can still use proof. Generally, it's safe to use proof without ampersand when it's the last time you'll ever need proof in this function. Otherwise, you borrow it, or you always borrow it. Now, at this point, we need to, we made sure that the hash doesn't exist, and we made sure that the sender is, that we can extract the sender from the origin, if the origin is signed. Now we need to find out what the current block is. So let's set a variable. And for that, we'll invoke the system palette that we've previously aliased. So that's going to be system, and we call on its module. And in it is the function block number. And this function will return the block number to us. Now, all that's left to do is to save this into the proof storage item. Proofs, and again, this is just the syntax that you have to get used to. And then you have insert, a helpful function to do this for you. Again, we need to borrow, because if we just put in proof, and we'll still need it to emit the event, remember, again, we need to borrow. And we said that we are storing a hash and a tuple. So we have our hash, and the second argument is going to be a tuple. So in this tuple, we put sender, and we put the current block. Notice how we're not borrowing the current block, because we don't care about using it later. We don't need it anymore. But we need the proof in the sender for our event. This is how we emit events. Self deposit event. We call the deposit event function that we defined earlier, this one. So that's self deposit event, this one. Deposit event in this palette. And inside it, we say raw event, claim created, and we give it the arguments that we have defined earlier. Claim created, account ID, and the hash. So that's going to be, again, sender and proof, only this time without the ampersand, because we no longer need to use these after this line of code. At this point, our create claim function is done. And before, like, instead of compiling this, we can use a helpful function. Whoops, this is still running. It's actually okay, that's still running. Let me check in another tab. So to not, like, compiling takes a while, and it's kind of slow. So to make sure that your code is fine, you can run cargo check. And cargo check is just going to go through your code and check that it works, check that it compiles without actually compiling. So it's going to be much faster. So now cargo is doing this. And while we're doing this, let's maybe copy all of this to our playground and see if it works there. Playground, let's edit. Where is it here? Palettes, template, source, librs. Dependencies from cargo toml. So the last two blocks are okay to be copied over. That's the, oops, let's not overwrite the last block. Okay, just the features. And we save. And now we can Is our node running? It is. Let's stop it and let's recompile the node. This is going to be cargo. You can see now that this one started. Oops, hold on. Unused import ensure signed. Looks like we have a typo somewhere. Looks like we have a typo somewhere. Let's find it. Ensure signed. Ah, yeah, okay. I forgot something. This is a new edition, so I keep forgetting it. Now, every function that you write in for developing these custom blockchains, to prevent denial of service attacks on your chain, to prevent spam, and to prevent people from issuing transactions too much and slowing down the chain, you need to have some sort of metering system, right? You need to make it so that people don't have, so you need to have a reasonable transaction fee system in place so that people's calls actually cost money, so that they can't just spam your chain. And in Substrate, this is done with weights. A block has a weight limit, which can be populated by the weight that is by the approximate weight. How to explain weight? Weight is kind of like the heaviness of the operation that is in regards to the CPU cycles that it requires. So there are some benchmark palettes available that you can use to benchmark your own code and figure out how much weight you need. But you can use the default weight in our palette here and just do it like this. So weight will be frame port, and that has weights. And in the weights, there's just simple info, and we'll use a default weight. So this is like the template weight for very like lightweight functions that you don't want to bother benchmarking. Like, of course, when you're writing production code, you'll be benchmarking this heavily and figuring out what you need to kind of like you'll be figuring out exactly what kind of a weight you need for your code. But during development, this is fine just to get your code to run. This is now compiling. You can see that it started from 652. This is because the cargo compiler will only compile from the changes that you made. It already pre-compiled all of the other stuff up until this point. But since we just changed one file, it'll just compile that file and all the other artifacts that result from this compilation, so the binary and the wasm blob and so on. And this is why compilation is much faster in subsequent edits than it is in the default, when you're starting from scratch. Looks like this is compiling successfully now. So let's also check how our local node is doing. This is also going to fail because I was missing the weight. I think it loaded the code before I added the weight, so it should fail, but it's taking a little longer here. There we go, it is moving now. And notice that our chain is still running, so there's nothing interrupting it while this is checking. So this is just the cargo check. But we'll also demonstrate, let's actually, while this is running, let's demonstrate that we have our function now in our development chain. So let's start this node. Let's purge the chain first. Purging the chain means deleting the database. Now let's start the node. Did I press compile node? Oh no, this is still building. Oh, all right. Still not done. So the compilation step of the binary is by far the heaviest. It's always going to take a few minutes. It'll depend on the strength of your machine, but it'll always take a few minutes. Okay, this is done. This is checked. All right, this is good. So this check has been successful and it works. But if we look at our chain, which is still running, let's reload. And we check our extrinsics and we check the template module, the old functions are still there. And there's no create claim function. This is because we haven't loaded the new runtime. It's still running on the old runtime. We'll demonstrate how to change that in a second. So let's see if our playground has finished building. Come on, playground, you can do it. Now let's start working on the revoke claim function while we're waiting for the playground to finish. So in a similar vein, we'll define the new function. We can just copy this weight information here so that we don't forget it again. So we'll also do revoke claim. And again, origin is always the first, and then we have which proof we are revoking. Now, to revoke the claim, again, we need the sanity check to make sure that our sender is who they say they are. That stays the same. But in this case, we need two more checks. First, we need to check that the proof being revoked actually exists. And we do this with now we make sure that proofs key, and again, same thing, proof. And if it doesn't, then we emit an error that is going to say that there is no such proof. Let's define that new error. This claim does not exist and cannot be revoked. Proof. Moving on. We're now sure at this point that this proof exists and that our sender is legitimate. But we are not sure, we definitely do not want to let somebody delete somebody else's claim. So we have to make sure that the sender is also the owner of that original claim. Now we said that we are storing the data into a tuple and account ID and block number into our proofs under hashes. And we can extract that from our database, right? We'll do it like this. We'll let owner and underscore, and I'll explain what this is in a bit, be proofs and get, and then we get the proof. What does this do? We know that get will extract the value, which is this, by key, which is this. That's fine. So we get a tuple back. We get this back. And by saying let owner and then underscore, we say, give me just the first value in whatever you get back from this and discard the rest. And the first value is the account ID. So we get the owner. So now we need to make sure that the owner is actually the sender. And if not, we emit an error again. We're going to say that not owned. It's going to be called not owned. And we'll say cannot delete this hash. Oops, I'm in the wrong in the events, sorry. Okay, now we have our errors and we've made sure that all the sanity checks pass. And at this point, we're ready to remove this proof. So proofs again. And proof. Again, we're always borrowing because we always need to emit the event at the end, and the event needs data about the proof. So we can't really discard it. raw event, and we have here claim revoked event, which we have defined earlier. Vendor proof. We emit who deleted what in this event. And our revoke function is also ready now. Let's save this. Let's see if the playground has finished to demonstrate something. It has. Now let's start the node. Wait, hold on. I've started too many terminals. No. All right. Keyboard shortcuts do not work the same way as on the desktop. There we go, there we go, there we go. And this is running. Let's close it down. Let's purge the chain. Let's actually close this down. And let's purge the chain. And now let's start the node. So the node is now running. Let's check out our remote connection to this playground instance. So like I said, where's our front end? Here. We have this URL here when we run the front end from the playground. So let's try and copy that, put that into our UI. We click custom endpoint and put that in. Save and reload. Let's see what happens. All right, block 5. Let's check out our extrinsics template module. Whoops, we have create claim. There's no more create cause error. There's no more do something. We have create claim. Let's check out if it works. We put 1234 as a hash, obviously not a real file hash, but let's check it out. We submit from Alice. Let's see what happens. Block 9 has triggered. Let's inspect block 9. Block 9 has the event, template module, claim created. Event is emitted when someone registers a claim. Our message is here, our event is here, our hash is here, our submitter is here. Let's check out if it's really saved. We go to chain state, storage. We find in storage our template module, and there we go. There we have our proofs. And now we can check for that hash. 1234. Let's check it out. And yep, indeed, this account, this is Alice, has registered this on block 9. Yay! Our saving works. Now let's work on revoking. So we have now built our revoking functionality, but at this point, we don't want to stop our chain. We want to forklessly upgrade it. And now let's look at how this magic works. So first, we're going to build our node. So it's going to be cargo build. Now we can see that it, again, started from a very recent state. And now it's building the node. Now it's building the node. All right. All right. Let me just shut this down. Okay. This should work much faster than the playground, so should have it done in a moment. Actually, this is just producing the binary, so we don't even need the binary. What we're going to do now is do this. Let's connect back to our local node. Custom endpoint off. Let's scroll down. Local node on. And you'll notice that there is this sudo option that I mentioned earlier. So the sudo is the admin key of your chain so that you can actually do whatever you want to do on it. And usually chains will start with a sudo module enabled. And then once the chain is stable enough and has the functionality it needs, the sudo module will be removed. And the chain will be decentralized. But at this point, it's centralized so that development can happen much faster. So we go to sudo. You can see that pre-selected, we have the system palette and the set code function. The set code, here it says, set the new runtime code. So we can upload new code here, and our chain will actually start running this new code. And what is the new code? Well, our new code is, right now, if we check, this is my development chain. In my development chain, my template module still has the cause error and do something functions. But once I upgrade the chain code, the code will actually the function will actually be changed to whatever we've developed. So create claim and revoke claim. But before we do that, we need to do one more thing that I forgot. And this is compiled, so that's great. We need to do one more thing that I forgot, and that is bump the spec version. Because the chain looks at the version of the code on the chain, and the version of the code in the native code. If the version of the on the chain is newer, then it will use the version on the chain. But if they're the same, it's going to be using the local one. So this wouldn't work right now. So now let's first go to runtime, source, and there's librs. So this is the librs of the entire chain. And if we scroll down here, we see the spec version. So let's increment this to 2, save, and recompile our node. Building. There we go. And this is already ready to run our stuff. Let's check it out now. So the WASM blob, so the blob of code that we want to upload to our chain is in target, release, wbuild, node template runtime, and this is the file, node template runtime compact wasm. So this is the file that we need. Let's find that. Let's do that. Let's go to our portal. Let's select the file. And you can now select to drag and drop the file here. Let's do that. Let's go. Repos. And we have here fresh, target, release, wbuild, no template runtime, and there's the WASM file. It's 212 kilobytes. Let's load it in. There we go. And now we submit sudo. We submit the admin command to upload our new code. Again, from Alice, because Alice is the only sudo account in this dev chain. When you run a development chain, Alice will always be the sudo. In your real chain, you're going to set sudo to somebody else, to a locked account. We're in block 604, it's sending, and in block 605, it was included. Let's see what happened in 605. It says sudo, a sudo just took place. We have successfully added the sudo code. But we don't have the code changed event, which means that this failed. This probably failed because the wasm wasn't completed yet before I loaded it in. So let's wait a bit after all, because right now if we reload, if we check our extrinsics, template module is still the same, right? Didn't work. So let's check this out. Let's wait for it to build. Okay, it just built. Now let's try and re-upload some new code. I saved the files. Yes, I did. All right, let's check this out. Okay. No, again, it didn't change our code for some reason. Let's try and find out why. Runtime, we have the spec version bumped. We have this. This all works. This is good. Let's increment all the versions. Let's see what happens then. Release. And actually, to speed this up, you can actually run just a sub command to build just the node template runtime. I'll demonstrate this in a second. Waiting. Come on, little buddy, you can do it. You can do it. Go node template. Go cargo. Go. Come on. Yeah, sorry, I don't know why it's taking so long. In the meanwhile, let's play with the front end. While we still have time. So if you've downloaded or run the playground version of this off the front end, let's try this out. Let me open a new tab. So Substrate front-end template. If you run yarn install, you should have had the dependencies installed, and then you can just run yarn start. And yarn start is going to start this basic front-end template that will open up in your browser automatically and load up your chain if it's running locally. You can also change what it's connecting to, but this is really perfect for local development. So this is optimized to connect to your local chain. There we go. So it's now reading my chain. It's saying that it's on block 647, finalized block 645. There's all the unlocked accounts that we've already played with. And there's a bunch of other accounts that are preloaded. And you can see here that we have some common functionality. Transfers to and from an address, upgrading the runtime. So that's the pseudo thing that we've just been playing with. Extrinsics, that we submit custom extrinsics. So again, this is still cause error and do something. And there's some chain state to check out database and so on. So template module, if we check out something, then we get the query, we get, does not take any arguments, one found. That's weird, it doesn't, okay. So this is the rudimentary UI that you need to modify to work with everything. So this is, but it did return the current value of 10. This works. This is something we played with earlier when we submitted a sample value to our do something method. So now if I do template module do something, if I put in 15, I call this gets called from Alice. You'll see an event here happen. There we go. And now the value is 15. That's good. So now you can see here that this template module, this is a custom UI built for this template module. It has a special UI part. So this is a special UI part where you can just put in the new value and it'll store this value directly. You don't have to call it through extrinsics. So if I put in 25 here, it'll store something. And you can see here that this is really simple, like a simple UI just for your custom palette. So let's build this for our custom palette as well. Now let's modify our wasm runtime if it's been built. It has been built. Let's see if the file changed. It didn't change. So my file is not changing for some reason, and I'm not exactly sure why. I would run, if we had time, cargo clean, and then recompile to get all of this compiled from scratch. But this would take upwards of 15 minutes, which we do not have. So you'll have to take my word for it right now, and believe me that this works. But right now, let's do something else. Let's do that custom thing. And to do that, to force that to happen, let's restart our node and it'll just inherit the new functionality. So first we'll purge the chain and start over, and then we'll just run our blockchain. And now if we inspect what we're getting in our local chain, there it is. Okay, it's on block 0 now, and proceeding to block 1. Go, little chain. Can't author. Probably no update is required. Yes, of course. That's because I changed this. Authoring version 1 will be this implementation version 1. And now I will need to recompile. But let's modify our front-end template in the meanwhile. This is some code that I can share with you. We're not going to be typing it out from scratch because it doesn't really make sense to do so. But it's already a pre-developed alteration of that component so that we can just use a custom UI for our chain. And this we can find in template. If you open Substrate front-end template folder, you'll find a template module.js file in the source folder. And you can just replace this entire file's contents, really. You can replace with a ready-made React component that we have prepared and that I can share later, but I'll just demonstrate it here. So I paste this in and I save it. And now the UI has already reloaded and taken into account this new template, but it's erroring out connecting to the blockchain because we're still building our node. So let me just real quick show you this. Actually, let me show you this on the playground. Let's modify the front-end template source, template module, everything, save, and now let's start and open the front end. So this is asking me permission to access my wallets in the Polkadot.js extension. The extension holds your Polkadot and Web3 and Substrate keys so that you can use the keys across many websites that interact with the Web 3.0. Now we have this, and now we have this. But our custom component is not loading because our chain doesn't have it yet. So we can't really use it just yet. Okay, let's rely on the local one. We should compile it faster. It would be much easier. If you have any questions, please put them in the Q&A because we're approaching the end. And if there's anything that you're curious about, I'm happy to answer anything that's unclear or that's maybe confusing. I realize that this was a lot to take in and there was a lot of new stuff, but it takes some getting used to, but it becomes very intuitive after a while, and then it's really a great thing. There we go. So now our chain is starting from scratch, and here we go. Our custom component for the UI is already loaded, and you can see here if I load any file, a random file, like this wasn't file, for example, I load it, it'll immediately create the hash for me, and it will tell me that it's unclaimed. The proof does not yet exist. So this UI element checks this for me, and then I press create claim, and it just creates that claim. It saves that hash. It makes the create claim, and there we go. We see the owner, which block it was created in, which hash, and we can see the event that also says the same things. And the event is just as verbose as we want it to be with a custom message. So you can see how easy it is to develop custom components that interact directly with your chain because the accessibility is there through the metadata. So because we are using in this code, in this user interface, because we are using Polkadot.js API, so this is the Polkadot API, this is the API package for interacting with substrate-based chains. And this package actually reads the metadata of the chain and is able to intuitively interact with the chain underneath based on those translated methods. So if you inspect this component that we've just built, you can see here the logic of this component. So we just find something interesting to show you here. So we have here the proof of existence function, and you have here use substrate. And now just this part immediately instantiates and helps the API interact with any substrate-based node. And it just works, like out of the box, it just works. So there's no complicated setup process. This takes a file and creates a hash from it using the Blake 256 hash function. And there's all the other functionality that you might need. And there's a check for the is claimed. So if the block on a claim is not zero, then the claim, the hash is claimed. So simple checks like this can make all the difference here. And they make it possible to interact with this chain very easily. And just by using this use substrate thing, this prepares all the methods in advance for you. So you don't need to write any of them by hand. It just reads from their inputs and outputs. Let me actually show you the metadata that I'm talking about. Portal, this is the development chain. Now if we go to toolbox, RPC calls, and system, and no, it's not system, it was state, and get metadata. And now if we query metadata, there it is. This is all the metadata, and this is everything that our chain returns. You can see here all the methods, all the functions, everything is described. And any UI and any API can actually read this, parse this, and use this to build an interactive interface with your code, right? So let me try and find our There we go, create claim. Create claim, and it says everything that it needs to say. It has arguments, the name is proof, it's bytes, a revoke claim, also proof, bytes. There's no documentation because we didn't put any, but generally we put a documentation there as well. You have here our events. You can see that its name is claim created. It has arguments, account ID, which is and account ID and bytes, and the documentation says the message of the event. So the UI will know everything it needs to know about our custom chain. And there you go. Like, congratulations, right? You have this functionality loaded, and your custom chain works with barely an hour of work. And check it out. Now we can revoke the claim as well. If I click revoke the claim, this claim was this was unclaimed. This hash that I just a minute ago that I claimed, this was just unclaimed. And I can check this out here as well. Extrinsics, system, template module. Alice can create a claim like this. Save it. Go. Now we can go check it out. Chain state, storage, template module, proofs. Let's make sure that this hash exists in the system. Ah, damn it. I was not supposed to click that button. That's the file upload button, sorry. Template proofs. All right, let's check it out. 1, 2, 3, 7. There we go. Alice registered this in block 45. Okay, let's try to revoke it. Let's try to revoke it from Bob. Bob can revoke claim 1, 2, 3, 7. Let's revoke Alice's claim. Revoke. Boom, error, not owned. Let's check it out. Extrinsic failed. And there we go. We have the dispatch error of type template module not owned, and the details are cannot delete this hash, you do not own it. Okay, let's revoke the hash from Alice. Revoke claim from Alice. And let's check out the chain state. Template module proofs 1, 2, 3, 7 again. Does it still exist? It does not. So it's a block 0. This address right here, this is the default address of the module, of the palette itself that we've built. So this is kind of like a null address, an unusable address. But the block number here is indicative of the non-existence of a proof, right? So we have successfully revoked it, we've successfully created it, and we've successfully made sure that nobody other than the owner can actually evoke a claim. That is it at this point. If there are any questions, I'll take them. Otherwise, we'll wrap up, and I will be happy to share any materials and details with you after the presentation. Just get in touch if you want to grab the slides or if you want to grab the code. I would also recommend you visit substrate.io. Substrate.io, which is our new development portal for learning how to build your custom blockchains. And if you go to substrate.io/tutorials, you'll actually find these. So this tutorial was a merge, was a blend of several others, but mainly this one, build a PoE decentralized application. This one is not as detailed, and it'll just drop some code on you without too much explaining, but it's a great way to get started. So each of these will take like 30 minutes to complete, but it'll get you started and it'll get your feet wet in Substrate and palette development. So I recommend you go through them and check them out. We also have the knowledge base and the Substrate seminar, which happens every Tuesday. It's live and it happens online, and we discuss new like Substrate topics, like things that people encountered or that people might not know, and so on. There's a lot of stuff here. There's the knowledge base that you can investigate, and really I encourage you to visit substrate.io for more information on all of this. And if you'd like to learn more about Baccarat Network itself, go to Baccarat Network and find out all the information you need there. We're launching the network soon, but in the meanwhile, we have launched Kusama Network. So Kusama is like Baccarat's crazy cousin. Kusama is the experimental network for Baccarat, which gets all the custom palettes, all the experimental modules first. It's not a testnet. It has its own staking economy. It has its own tokens, which are not worthless. And it actually works. It's a great blockchain. I'm a big fan of it. And it's kind of, it's very daring. Like it likes to experiment. It's not afraid of change. It's not afraid to break things and you know, to make chaos happen. So Kusama is a great ground for your experimentation and to interact with. And we have all of this described on the wiki. If you go to wiki.baccarat.network, there's also a Kusama section which will explain this. But the chain that we've interacted with at the start, it was Kusama, in fact. And you can see here that there's already a lot of stuff in progress, right? There's the Treasury, which currently contains 171,000 KSM. This is around $1 million in value. And there's various proposals on how to spend this on-chain Treasury. And the Treasury is a custom palette developed for holding funds on the chain itself and for funding the ecosystem. The democracy is voting for changes on the chain. There's the Council of Trusted Users on the chain. There's a lot of different things you can explore, and you don't need money to explore all this. So I encourage you to go to baccarat.js.org/apps to explore Kusama and join us in this crazy new ecosystem. Thank you very much for your attention. Please let me know if I can help with anything after the presentation, if I can share any code with you or any links that you're interested in. And otherwise, I hope to see you again in another tutorial somewhere else. Thank you very much. And thank you to the organizer for this amazing event. Cheers.
Thank you, Bruno, for taking the time out of your day. I just want to leave it open for maybe a minute or two just to make sure if any of our attendees have any further questions, feel free to post in the Q&A or the chat and we'll get those answered. If not, this recording will be uploaded probably in about 72 hours or so as this conference concludes. All the information, including Bruno's interview from day one, is available on the website. You can catch him during his talk. And I think that concludes it for today. So again, Bruno, thank you for your time, man. And I hope we can catch you again soon. Thanks for participating, in the whole week.
Yeah, thank you for having me. Bye.